Hey, what's going on YouTube? What's up? So, I'm stoked to be streaming again today. It is the fourth time that we're going to do one of these math streams, so I'm excited. We've done three so far on some elementary number theory. So I've introduced like the idea of Fibonacci numbers. I showed like a couple of things I like to teach kids that I'm tutoring, like even the Collat's conjecture, I think works really well with kids. And then over the last couple of streams, there was like a nice coincidence where I introduced proof by induction in two streams ago. And then yesterday, a friend texted me about an awesome identity. And I was like, oh, that's so cool. I just proved that on the airplane on the way back from holiday vacation. And it is a fact about the number 2025. So today's January 3rd, 2025. This channel is brand new in 2025. So that's fun. Today we're going to switch gears, and it's going to be different on two different fronts. One, the subject is changing. Today we're going to do linear algebra instead of number theory. And then secondly, today I want to try my first practice stream. So instead of it being a lecture and me just working problems I've already solved, I'm going to shut up, I'm going to stop yapping, and I'm actually going to practice some linear algebra myself. But every video, I want to try to have something for everybody. I want to have something for all different skill levels of math. I'm not advanced. I'd say that I can probably start studying at the graduate level, like a master's degree. But I'll also be working a lot of problems from undergrad books too. But I also, not just graduate math and undergrad math, but I also want to have something for everybody, including kids or adult hobbyists or adults who haven't seen math in a long time, and this is the first time that they're ever exposed to the idea of pure math or people who do math for fun. And at least for these first videos, I should introduce this with what the hell is going on at all. My name is John. I used to study mathematics before working in Silicon Valley for the last 10 years. Now I'm reviving my love in math, and just now I'm no longer studying it with the goal of getting into academia and doing research math, becoming a mathematician, becoming a professor. That's a really hard life. That's a very hard life, I think. Now I'm just studying math for fun because I love it and I think it's very beautiful. And so I want to share the journey with you all. The other thing I'll say is that I'm porting over the entire concept of a practice stream, which is something I've been doing for the last 5 years in classical guitar. So if you are interested in classical guitar, you can find my channel, JC Practices. This one is JC Practices Math. And yeah, I haven't set it up yet, but in a moment we'll be listening to one of my guitar recitals as like the background music of this stream. So my weird concept is that maybe the two channels can have some crossover. I'm able to get some people to come over from the math channel or from the guitar channel to this one. And then maybe some people here might be interested in classical music as well. But more importantly, guitar to math. So something that I want to have for everybody is two ideas. One is there's this funny joke in math, and my friend who texted me the 2025 fact also echoed this exact same joke, and I was like, I'm glad I'm not the only one who tells this joke. There's a funny joke that in math, as math gets harder, it sounds easier and the books get smaller. So, like when you start out with math, you learn arithmetic, and then you learn algebra. You do algebra 1, you do algebra 2, then you move on to trigonometry. That sounds way harder. And then you do calculus, and that sounds way harder than either of those. But then when you go to college, if you're an engineering or math major or computer science, you study linear algebra. And it's always funny because I would tell people that, and like, I love linear algebra. And they're like, that sounds like semester 1 of Algebra 1, right? Like studying lines like mx plus b, and studying like a line. Like, isn't that super easy? It's actually harder, and it's actually more abstract than Algebra 1. And then after that, I don't know if it sounds easier or harder, but then the next course is typically modern algebra or abstract algebra. Maybe that sounds a little harder than linear algebra, but still, a lot of colleges will just call that class algebra, especially at the graduate level. Like when you do master's level math and you're a graduate student and you're super stressed out, preparing for qualifying exams and whatnot, and people ask, oh, what do you study? And you say algebra. They're like, I took algebra like a long time ago when I was like in freshman year of high school or something. Like, I took algebra. I took college algebra. Like, what do you mean you're studying algebra? So I think that's funny. For example, these two books. This one is very famous. This is Dummett and Foote. It is a upper division undergraduate abstract algebra course. It could also be used for like a first year graduate course as well. But often at the graduate level, you'll work from this book. And instead of it being called, let's get it to focus, damn it. Instead of it being called abstract algebra, which sounds kind of hard, come on. Instead of it being abstract algebra, now it's just literally algebra. That sounds easier than abstract algebra, right? But then, to take it in an extreme, the scariest book, I think, of all time is A Course in Arithmetic. This book is scary as hell. Like, you read the first sentence, and the very first sentence took me a while to understand. And it's just so full circle. It's like you start out learning arithmetic when you're really young, and then later on, as you get farther into math, you're back to studying arithmetic. And not only that, but the books are bigger, and then they keep getting smaller. The smallest books are the scariest books. Which kind of brings me to another topic. Here's one of the books that I just purchased. And this is a scary book. It's tiny. It has no exercises at all. It's just math. And it's all about this abstract algebra concept of Galois theory. But I said that we're switching over to a new topic. This is one of the books that I just purchased. Let's define the goal of the stream in every introduction of these streams. Here are a bunch of books that I just purchased. Look at all these. Look at all these beautiful books. Look at all these topics. Moscow Puzzles, Shortcut Math. I think that these right now are roughly ordered in difficulty. Not really, no. These are unordered. But yeah, so some of these books, like Shortcut Math, this is literally arithmetic in the elementary school level. Like, this is literally just how do you multiply two numbers quickly, or how do you add numbers quickly, which is pretty fun stuff, I think. I haven't even read this one yet, or I haven't even opened it yet. It looks really great. But yeah, so the point of this channel is we're going to solve every exercise in these books, which are all brand new for me, as well as a lot of other books that I have. Part of this is inspired by the fact that I have recently been tutoring a student in calculus. I've been tutoring again for the last year. Oh, shit. Okay. Apologies for my language. This is a PG-13 stream. That's my one... Oh, no, yeah. PG-13 movies can swear multiple times, but you can only get one F-bomb, I believe. So I'll get one F-bomb per stream. How about that? So I've recently been tutoring a student in calculus, and I want to say that this book is beautiful. This book is incredible. This is freshman calculus. And just like algebra, it gets scarier as the name sounds easier. But this book is fantastic. I've never seen this one before. It is at the level of Stewart, which is like the most well-known calculus book, and it's good. A lot of classes are taught from that. But this one, Taalman and Kohn, this one is beautiful. Like, it just doesn't have all the like cartoon images on the sides. Like, it has some tasteful amount of color in the pages, but it doesn't have all the marginalia that the other books have, and it has just ever so slightly more emphasis on theory and proofs. But the exercise sets, like, look how nice this is. The exercise sets, like, here is I don't know, I just randomly opened to a section on L'Hopital's rule, which is how you calculate things like infinity raised to the infinity. Like, what would that be? Or infinity raised to the zero. What would that be? If you look at the organization of the problem sets, they are organized with a section that is like a review section. There's a section that's called concepts. That's a really nice organization on this. Concepts, skills, applications, proofs, and thinking forward. So, like, all of these problem sets are organized well, so if a teacher wants to emphasize proofs more, they can pick the problems about proofs, and every section of exercise sets has seemed that way, like, organized really nicely. So, what else? There's like a little bit of fun flavor about how math books, as they get harder, they get scarier. Or as they get scarier, they sound easier. Like, university freshman engineering math is calculus, but then math major math, it's the same topic, but it's called analysis. And that sounds like it could be anything. Like, analysis sounds like it could just be, I don't know, analyzing, analyzing how many acorns are outside. I have no idea. And then, so, again, like, they get thinner, they get smaller. This book is way scarier. We use this in, like, second semester graduate analysis when I took analysis. It's not easy, but medium, hard, harder. Let's call it that way. So I love it. Oh yeah. And last thing, sorry for the noise. I'm so bad about dropping things right next to the microphone. One last thought. Dover books. All of those books I just showed that were brand new for me, all Dover books. And I just want to express such gratitude to the Dover Publication Company, because they're cheap. They're just like $20 each. And they're often reprints in paperback of old classic textbooks. Whereas like these nice hardcover books are beautiful and lovely, but they are often expensive, like $60, $80 or $100 or $200, depending. As math gets harder, the books get cheaper and smaller, and they sound easier, which is funny. Cool. All right, so that is just like a little rant about Dover books, about easy versus hard math books, and a tiny bit about linear algebra. So I don't know if I'll be able to define linear algebra a little bit more carefully than this. We will. Let's do it. All right, so we're going to switch over to the iPad view. If you see the last couple of streams, we were on the iPad the entire time. Right now, we're going to switch over to the iPad. It takes a moment here. So everything is live as part of these live streams. I find it very important. I have a lot of lessons and maturity that I've learned over the years from working in the real world, working at Apple, Lyft, and Google as an iOS engineer. I have a lot of lessons and maturity that I've learned over the years, and one of them is like, just get it done. Like, just ship, just get it done. Like, it's not ever going to be perfect. Don't worry about it being perfect. Just get it done. And it's okay. It's better to be done and sloppy sometimes than, not done or late and imperfect. Or late and imperfect. Like, the phrase in software is shipping beats perfection. And so these streams are going to be a little rough around the edges every now and then, but, other times they're going to be nice. Back to linear algebra. I'm going to just practice and study right now. We'll pull up my guitar recital and just listen to some music, and I'm going to start practicing. So this is the linear algebra book I just purchased from Dover. It's beautiful. It's really beautiful. Like, I really like it so far. It's not the book I wanted, though. Because I'm pretty rusty, I wanted a more computational, first course in linear algebra. And I thought that was this book, but I didn't read the reviews, or I didn't really read about it at all. I was just like, $20 or $15, yeah, sure, I'll get it, whatever. This is actually more of an advanced linear algebra book, but it's really beautiful so far. Like, I'll just have to get another one. So if I can get the iPad on screen, I can start defining what linear algebra is just a little bit more carefully. So linear algebra, as I said before, it actually is related to lines. Like, otherwise we wouldn't call it that, right? But it's like, think back to your college algebra or Algebra 2 study days, and I think most people have seen the problems about solving simultaneous equations. I am trying to see, how can I screen? Okay. All right, so I'm going to try to get the iPad finally on screen before everybody drops off. I doubt anybody's going to see this video for a while, but I hope that it's interesting way after the fact. At least the intro was, I don't know, I think that's relatively evergreen content, talking about how great Dover books are and all that stuff. So iPad is mirrored. Let's get... Okay, we've got a brand new math OBS scene. Is this working? I think it's working. All right, but where's my Apple Pencil? Here it is. All right, so before I lose everybody, let's start listening to some music. Here is my guitar recital. Yeah, I want some music. Nobody in the chat. Let's check chat, see if anybody's there. Of course not. This is a brand new channel. Nobody knows I'm here. The other one is really growing, though. I just crossed 1,000 subscribers, and recently they've been really popping off. I got monetized. I got a tip jar, so that's cool. I wish I had a tip jar from day one on this new channel, but nope. That's a little ridiculous if you ask me from a product perspective. I think I have OBS set up now to stream audio correctly. Music only. Dang it. You know what? I want to listen. In another video, we listened to one from a while back. This time around, I want to listen to my playlist. You can get to this by rcm.jcpractices.com. And yeah, so this is my debut EP as a guitarist. Guitar is my hobby, same way math is. It's my deep hobby, I like to call it. All right, I have no idea if the audio levels are fine or not. It's good for me. So, linear algebra, let's get started. Today's the 3rd, 2025, and the topic is linear algebra. Okay, so I have not studied linear algebra formally in many years, and we'll see how this goes. So let's make sure that the iPad is constantly refreshing correctly. Well, recall this problem. It's called a system of equations. I don't know. First, we have one equation, y equals 2x plus 3, and y equals 3x plus 4. Solve for xy. So this type of problem, I think most people have seen, and you can do it a few different ways. You can, well, all right, so if we already have it solved in terms of y in the first equation, maybe we can, let's say, solution. Replace equation 2 into equation 1. That's not perfect, but we know y is 3x plus 4 in the second equation, so we can put that in the first equation. 3x plus 4, we can replace y in the first equation here. Then all we do is just solve for x. X equals -1. So I subtracted 2x from both sides, and then I subtracted 4 from both sides. Then solve for y. So recall y is 2x plus 3. So then y is 2 times -1 plus 3, which is -2 plus 3, which is 1. That's if we used the first equation. But what if we use the second equation? Well, the goal here is that the same solution should work for both equations. Let's just double check ourselves here. 3x plus 4 instead of 2x plus 3. This is 3 times -1 plus 4. hey, minus 3 plus 4, that also equals 1. And then you can also just double check yourself to see that plugging in x equals 1 in both equations works as well. Or just from the very beginning, we can see that the solution x equals minus 1 and y equals 1 works. You can just plug in those numbers, x equals -1 and y equals 1, to see that both equations are solved at the same time. So that's great. We're done. Here is an example. Let's think about it geometrically. I said that we're solving simultaneous equations, and linear algebra is about lines. So the first equation we had, let's just take a look at the same ones. 2x plus 3. It's going to be a positive slope, and it's going to start somewhere above 0, 0. Y equals 3x plus 4. Okay, that's going to start a little bit above the other, and the slope is going to be steeper. That's not perfect. In fact, that's very much not perfect. So here we have y equals 2x plus 3. And then we want another line, y equals 3x plus 4. Let's make this more exaggerated. So they do not cross at the same y-intercept. But this one is going to be steeper, and it's going to have a higher y-intercept. Recall that 3 is a slope there, and then 2 is a slope in the first equation. And then the second number is the y-intercept. So they have a solution somewhere where x is negative and y is positive. If we look back at the prior problem, we found that the solution was x equals -1, +1, or xy equals -1, +1. And perfect, that matches. X is negative, y is positive. X negative, y positive. Cool. So there's like our motivation. This is the very beginning of linear algebra. We're solving systems of equations. And I just want to confirm nobody's in chat right now, and that's fine. Let's move on, and I'm going to just jump in difficulty. Linear algebra is taking that idea to an extreme, and you can have an infinite number of lines in infinite dimensions. So you can have not just two-dimensional, but also three-dimensional. You can solve 3 equations at once, or n dimensions. And what to me is beautiful about linear algebra is it's incredibly useful for artificial intelligence. Artificial intelligence is linear algebra. Linear algebra is one of the most useful uses of linear algebra is doing predictions and statistical analysis. Like if you have a bunch of data points, you can fit those to a best fit line. Well, again, there's a line, so we're doing some sort of linear algebra. Here, if these are all your random data points, if those are all data points, well, maybe those are Reddit articles on the internet and an incredible amount of data out on the internet that an AI model has trained on. AI trained on data. right? ChatGPT. Think of ChatGPT. And each of these dots is a Reddit or Quora or whatever article. What ChatGPT is doing is creating this best fit line. This is all so hand-wavy, but it's fairly accurate. And then when you ask it a question, it's a brand new data point, and ChatGPT is saying, oh, well, I don't know. It's probably going to be right here. Here's probably the right answer. Right in between, like, your data point is, like, similar. Your question, let's just have one question. I think that makes more sense. Ah, dang it. You have one brand new question that I've never seen before, but the pattern of all the other questions that are similar fits this red line. So here's my answer. And that makes something interesting because this is a hallucination. Hallucination. It's really close. ChatGPT is really close to the right answer, but it's always just a little bit off. And the game right now that everybody's playing is to try to make that smaller and smaller. Like, that was a bigger distance in the older AI models like GPT-3 or GPT-4. And now with O1 and O3, that distance is getting smaller and smaller. So it's really amazing. But what I wanted to say is in linear algebra and in AI, AI is not two-dimensional. It's more like, I have no idea, 400 quadrillion dimensional. That's pretty rough, hand-wavy. Oh, hey, stand strong. How's it going, man? No worries about joining late, dude. Thank you for tuning in at all. I didn't expect anybody to watch. Later on, you could rewind the stream. YouTube has a fantastic feature where you can rewind and do a replay. I think that the beginning of the stream was pretty fun. I talked about Dover books and some other cool things. Let me know how the music level is compared to whatnot. Today, the topic is linear algebra. To me, one of the most beautiful fields of math. It's perfect, great. Happy to hear that. Have you studied linear algebra at all yourself? So I did a tiny bit, just motivating. Linear algebra is this kind of system of equations. We want to solve those two lines at the same time. Where do they intersect? But now I'm saying that linear algebra is not in two-dimensional space. This thing is in two-dimensional space. Linear algebra is in 2 quadrillion space, or any number. And studying how to solve a quadrillion equations all at once. And so for all of our finance bros out there, NVIDIA and the other chips are making a lot of money. NVIDIA. And it's because they made the original graphics cards that were used for video games to calculate video games and video game graphics. So calculating like 3D objects uses linear algebra tremendously. I'm following Siri. It's a great concept. Thank you, man. Thank you. I don't know your pronouns, but I'm going to assume man because of my implicit biases. So NVIDIA is the company, one of the companies that has created these graphics cards. Linear algebra is used amazingly, like just constantly, to calculate 3D graphics. But then it turns out, oh my god, okay, this thing that was just fun and they were just games is now also incredibly useful for AI and ChatGPT and things like that. And the reason that it's useful for both of these is that we'll show what this means in a moment. Graphics cards are great at calculating these large matrices. These are kind of like numbers, but, you know, there's a quadrillion rows and a quadrillion columns, but you can think of like a huge grid of numbers. But there's many of them. It's humongous. Graphics cards are great, very efficient at doing these calculations fast, really fast. Originally for video games, now for AI, and now all of a sudden NVIDIA is worth a lot of money. So, anyways, that's our flavor. That's introducing linear algebra, and now we are going to switch gears completely, and I'm going to be live studying. This is the first live studying, live practice stream. And we're literally just going to listen to some music on repeat. Good question. So is it like millions of algorithms working together? Yes, I think that that's accurate. All of my understanding is rough, like it's just like surface level, but I think that that's accurate. A GPU is exactly like, it's very efficient at taking this and saying, let's use just a few numbers. Like, let's say that there's 10 calculations that you want to do at once. If there's 10 calculations you want to do at once, you can tell one undergrad, okay, solve these 10 equations. Or you can tell 10 undergrads, each of you solve one equation each, and then recombine, and then come back together, and then combine them, and then turn in your homework set together, and give each other credit, of course. So GPUs are very good at parallel computation. Parallel computation. So that is, and again, it's not 10, but it's millions or quadrillions of tasks going on at once. Not quadrillions, but many tasks all being calculated, numbers that are being calculated at the same time. That's what makes them very good at calculating these matrices and these numbers. So, yeah, great question. Now we're going to switch over to the live studying stream. But here's my twist. I want to just Command F and replace the word studying everywhere with practicing. It's my shtick. Like, I love the idea of practice, and I always try to use the word practice instead of study when I teach my students that I'm tutoring, because practice is everything. Like, you want to practice if you want to get good at anything. Few people call it studying guitar. You usually say practicing guitar. And to me, it's a slight mindset shift about the goal. And like practice, you can practice well all the time. I don't know. Those are loose thoughts that I'll connect a little bit later. But yeah, we're practicing here. It's not perfect. We're not studying. Somehow to me, like, it feels like you can study wrong. Like, you can study and not get it. Whereas you can practice, and maybe you didn't practice perfectly, but you still practiced.
Hey, what's on YouTube? What's up?
I need to shut up. Okay, there's my, I forgot to click the loop button. All right, so before we really finally get started, I also want to say to our new friend, I forgot your name already, Stand Strong. I'm very proud of my video from yesterday, so go check that out. It's a great video, I think, about video yesterday was about 2025. I love this. Somebody showed this to me. It is 1 to 9 squared, and it's also 1 cubed plus 2 cubed plus ... 9 cubed. Which is on its own kind of a cool little fun fact. But what I love is that I had just proved that exact same formula, not just for 9, but again for any number of dimensions, in a sense. I had just proved that in this book. So cool, you saw that video. I think it's a great proof by induction, and a great way to show proof by induction in context of such a fun, timely fact about 2025. All right, so let's come back to I want to get back to RCM, to my playlist. Or we could listen now, since we did just get through that one, which is pretty fun. Let's listen to our most recent recital next. This one I call Luna's Concert, and it's because my cat kept photobombing the entire time. Okay, cool. So, now, this is a new book that I just purchased by Shilov. And it's way harder than I expected it to be, but it's really beautiful. It's not the book that I was looking for. I wanted one that was computational. I wanted one that was like more about calculating matrices like this, like more engineering. But this is more like a pure math book. Which is beautiful and lovely in the other way. But linear algebra is great because it's both beautiful and pure math and math for its own sake, as well as incredibly useful for engineering. So to me, it's, I don't know, it's like it's the perfect math. So I'm going to literally just jump right to the exercises. I have not really read very much of this book yet. I'm just jumping right to the exercises, and we're using the exercises to motivate us. So, discrete mathematics. We will do discrete mathematics, absolutely, but I don't have a book at the moment on that. Okay, so problem 1. I love this. Like, this just jumps right into some hard stuff. With what sign do the terms A23, A31, A42, A56, A14, A65, that's going to be the first problem, and then a 3, 2, a 4, 2, or 4, 3, a 1, 4, a 5, 1, a 6, 6, and a 2, 5 appear in the determinant of order 6. So I took one look. That was the first thing I looked at when I just like skimmed and found the problem set, and I was like, oh, this is the wrong book. This is not the... This is a lovely book, but I already have a pure linear algebra book. I was looking for a calculational one. Oh well. Yeah, so this is a cool problem though. So we're gonna work through it. No idea. Yeah, I mean that was my thought too. I don't even think that I saw that. Have you done... You said yes earlier. Was that you, yes, have studied linear algebra already? Great, if so, because then you get to learn this as well. So, I remember calculating determinants. If you have, from the book that I used, which was in my class, which was Frale, which was a lovely book. I really liked it. You calculated a determinant and wrote it with these bars. I like using the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9 everywhere I can. That matrix, the determinant, first let's say the determinant, in a sense, we define it as the thing that tells you if a system is solvable. So that's going to be great. Like if we have some sort of machine that we can run and tell us if the problem is solvable at all, that's great. I want that. I totally want that. If I can find, we are solving multiple equations just like this. And like, wait a minute, what do you mean that they can't be solved? Sometimes you can have two lines that are parallel and they never cross. Like those two lines will never cross. They're parallel. Or sometimes you have two lines and like, oh, it's actually the same damn line. It's just written differently. So the determinant helps us understand which of these cases are we in. Are we in the case where we have two separate lines that will cross at a point? Are they parallel or are they the same damn line? What I remember learning was that and literally I have not tried this in 15 years or something, so I could be wrong, but I think that this is the way. What you do is you write the first few, you write the matrix again, 7, 8. You create this kind of like weird little virtual matrix thing, and then you go diagonally like this. The determinant wait a minute. Is it that? Yeah. So the blue lines are positive, or cyan, or whatever they are. The cyan lines are going to be positive, and the yellow lines are negative. So what do I mean by that? And what the hell is going on here? With those lines, what we're doing is multiplying 1 times 5 times 9, and it's positive. So I'm going to write all of the positive terms together, and I'm going to add those. 2 times 6 times 7, and 3, 4, 3, 4, 8. I'm going to switch to the dot notation. Then we subtract the yellow lines. 3, 5, 7. Since I have brackets, I'm going to... Here. Let's do this, actually. Let's keep the negative sign on all of them to be very explicit. So no bracketing yet. So we're subtracting 3 times 5 times 7. Again, that's this first yellow line. 3 times 5 times 7. The next one is 1, 6, 8. And then we subtract 2, 4, 9. Okay. Let's just do it just for fun to feel good about ourselves, that we still remember some math. 12 times 7 is 84. Is that right? Yep. 12 times 8 then is going to be 84 plus 12. Which is 96. And then we're going to subtract 15 times 7. 15 times 7 is 105. And 6 times 8 is 48. And 8 times 9 is 72. Now, whatever that is, pretty sure, I don't know, let's ask ChatGPT or a calculator or something. But the only thing that matters here is I'm pretty confident this is not 0. If you look at those numbers, I don't think that those numbers are going to add up to 0. This is the part that matters. If the determinant is not 0, then the equations are solvable. Cool. Stand strong. I have a question. The plane needs to be following Euclidean geometry. That's a great question. I think so. I believe so. But in math, every time that there's like a restriction like that, like we assume Euclidean geometry, which kind of by nature of talking about vectors or lists of numbers, like earlier I did a problem where xy was 1, -1, or -1, 1, or whatever it is. If you have like a list of numbers, a 0, a 1, ... an. Anytime you have a list of numbers, I think you're kind of assuming Euclidean geometry. That is what like Euclidean geometry is. It's about having a coordinate system, like x, y, and things like that. I don't know anything about non-Euclidean geometry. Not yet, but we'll get there. That might be in some of these books. For anybody else who might see this in the future, I think that this is an interesting aside. Geometry starts with the study of shapes. Like, circles and squares and triangles and pyramids, and that is all in the real world, roughly. But then in the early 20th century, I think, or late 19th century, some mathematicians discovered that there were some very interesting other types of geometry that are not in the real world, quote unquote, that are not standard shapes, but you can remove one of the assumptions that Euclid had, and then you'll create a whole brand new amazing field of geometry that's non-Euclidean. And that's all I know. Yeah, we'll leave it at that. That's all I know. But in the 20th century, last thing, in the 20th century, we started creating other types of geometry. I would call topology another type of geometry as well. And topology is about studying some other interesting shapes. And in a similar way as how non-Euclidean geometry removed the idea of a coordinate system and parallel lines and things, topology doesn't care how far apart two numbers are. You literally consider a coffee mug the same as a donut because they both have exactly one hole in them. So that's a whole other topic for another day. But that's one of those fun facts, I think. So yeah, great question. Thank you for asking that. Cool. So we're back to the determinant. This is how I learned it in the past, and it was very computational. It was like, let's calculate what this matrix times this vector equals. And then the class went into more abstract vector spaces and other ideas. But this is the type of determinant, and these are the signs, like positive, 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 negative, 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 that the question is asking about. So I'm going to go ahead and yoink, lift all of this. Let's try to lift this and move it down here. Oops. Hey, we got it. Oh, no. I was just moving it still. Okay. So now we are trying to understand what the hell this problem is asking us. So then I went back in the book and I learned and remembered some interesting facts. So they didn't... I'm going to revisit the book and actually write it exactly how he wrote it. Soon I'm going to be talking a lot less, and we're just going to be writing math. I thought that this was a really interesting, neat presentation. Okay, so when I'm solving problems, nowadays I've been mixing in my notes from the chapter, and I call that theory versus an exercise. So right now, I'm going to take notes on the relevant parts of this exercise. And I'm going to write out one part that's relevant and interesting. And I'm just going to copy it verbatim. Like, the physical act of writing and just copying a sentence verbatim helps you over time. You're going to move from just purely memorization and just like, I don't fully understand this, but I can copy it. And then once you've written it down many times, you'll be able to write it down faster, or you'll be able to summarize it, or you won't need to revisit that note anymore. That is like spaced repetition, which is great. So I'm going to, literally just level 1 copy exactly word for word what this says. We've got ... in section 1.31. ... is, I omitted a bunch of stuff, and then we say, consider in a matrix A11, A12, ... A1n, A21, A22, ... A2n. So yeah, just right off the bat, we jumped into abstract any number of entries type of linear algebra, and that's not what I wanted. But that's okay. It's beautiful in its own way. And he also uses this funny double bar notation, whereas most books use brackets, but it all works. That part seems pretty interesting. I remember that that's interesting, and then there's going to be there's like a little bit more discussion after that I'm going to skip. But let's pause here for a second and talk about it. So I think I'm having a couple thoughts here. One is a tip to anybody. It is worth taking notes, first off. Just take notes, write out things verbatim. It's a physical act of handwriting that helps a lot for drilling things and getting it into your head. Also, keep rewriting the same thing again and again. Like rewriting these notes for each exercise where you have to remember it is a good way to repeat and keep practicing, like revisiting the theory. I mean, and then how do you know what to take note on versus not if it's your first time through? Well, one clear signal is anytime that there's like an equation that's numbered like this thing has a special number, or maybe it's centered, like in this one, it's indented in the center of the page. Those are going to be important. Like, write that down. So that's one thought. Another thought is, when I started reading this, I do not like this notation. I feel this was a bad notation on his part, and I remember the books I used in the past would have used something like maybe I1, a I2, a I-N-N or something. Like, typically, the other books I've seen used I-J. They used I and J as those subscripts. And you would, like, a short way to write this big matrix is just bracket AIJ. Like, you don't need to write it with all the dots all the time. It's like I and J are the two subscripts. And so this can be A00, A01, A10, A11. Apparently I've turned into a programmer because I always start from 0 nowadays by default. But you get what I mean. Yeah, what I really don't like about this notation is that A alpha, like, that bothers me all the time because they both have like a round shape like this, and alpha also has that round shape with like a little extra tail. Like, that's just, I don't know, that I find kind of sloppy. Like, I find that a little, like, hard to visually see and read. Like, it makes this notation look scarier than it should be, I think. Like, this notation is way cleaner to me. Oh, Stand Strong, I saw that you had a question, but I haven't read it yet. Don't worry, like, I will absolutely read it just in a second. Please ask it again. I would love to answer it. Okay, so yeah, let me just put a bow tie on that and say a comment on notation. And the differences in this is a relatively old book from the 50s or 60s, and the newer books, I think, always use this notation instead. To me, it's way cleaner, it's easier to read, etc. Now let me answer your question. Sir, how can we become good in mathematics in general? Like my classmates do problems easily, which I face difficulty in. That's a fantastic question. No problem, sir. Teaching is priority. I mean, teaching questions are the priority, I think. Like, the best way to teach is when somebody has a question. So thank you for your question. Practice. Yeah, that's my answer. One word. That's it. Practice. That's the way to get good at anything. So there is a theory on practice. The same way that there's abstract theory on there is a theory on practice, the same way that there's a theory on linear algebra. Linear algebra is useful and it can be applied to make people a lot of money with with AI or video games, but it can also be studied as theory and like, why does linear algebra work? How far does linear algebra go? What are the limits? Can we use linear algebra to study non-Euclidean geometry? That's a great theory question. And so I could answer your question in terms of practicing mathematics, but to me that's like studying the application of practice for math. And then you get really good tips, like I like this tip for sure, which I'm coming up with on the fly. Like, I would say when you're solving your problems, take notes on the section while you solve that problem. Don't have two separate sections in your notebook. Like, all of my notebooks, I like to create a separate section for different topics. Like, I'll number my pages and say, like, starting on page 50, I'm doing apparently Sudokus. And then, like, starting on page 1, I'm doing linear algebra. I used to always have a separate section. Maybe the beginning of the notebook is theory and notes, and then the middle of the notebook is exercises. I've switched my method to mixing the two together, and that's been helping. It's brand new. We'll see if it sticks or not. Maybe I'll go back to the old way, but that's one tip of applying like a practice tip for mathematics. That is one way to get good at math. Let me write down tips on studying and getting good. Everything in the stream is, of course, in context of math. So I'm going to put that in parentheses. 1. Let's go simpler. Do lots of exercises. Lots of exercises. The way to learn math is solving problems. You can't learn math by just reading a book. You have to actually work the problems. So that's why now that I bought this new book, I just jumped right to the problem set. Like, I didn't read the section at all. I just went right to problem 1. And then I was like, oh, this is a different problem than I expected. I have to go back. And now I'm reading the section and I'm learning what I need to learn from the section. That works to a degree. That works better if you're revisiting a math book. But anyways, like, do lots of exercises. And a corollary of that is including I wish I knew this when I was in college. I didn't learn this until later. If you want to get good at math, and if that is your goal, maybe you want to study engineering or something else, and you want to get better at math, solve more problems. Not just the ones that are assigned for your homework sets. Solve more. Solve the ones that are not assigned. Do lots of exercises. And it's okay if you're not perfect at them. At least you tried. And it gets your mind thinking in that way. And maybe later on you come back. I would say repeat old exercises. for example, you can use Anki or any other flashcard app. Flashcards, like once you solve a problem, put it into a flashcard and then later on review that answer. Even if you're just skimming them, just go back and review them with flashcards. You could use an app, or you could literally just use paper index cards. Whatever works better for you. I'll make that explicit. Either way, an app or paper cards. Repeat old exercises. And then what else did I think of? These are all things that I did not do, and I wish I did when I was in undergraduate studying math. I did not go to office hours nearly enough. And work with others. Really, these are two of the same idea. Work with others more. Don't just work on your own. Solve problems with classmates. Create a study group and actually work problems together. You can do things like say, okay, I'll solve problem 1, you solve problem 2, you solve problem 3. Tomorrow we'll come back and we'll all share and teach each other. Like if you all solve one problem separately, and then you come back and you teach each other the problem that you learned, that's a great way to get a repetition and practice that problem again. Like they say that the best way to learn something is to teach it. Therefore, here I am. Here I am trying to teach math to random people on the internet. It's because I want to get really good at math. I want to get really, really good at math. So you don't do this for every class that you're in. You don't do this for everything that you want to learn. But the ones that you want to get really good at, you have to repeat stuff. You have to teach others. You have to do more than what's assigned, etc. And, even if it just means that you don't feel confident yet for the exam, like if you're just practicing for an exam like the SAT or the JEE or your final exam in a class, you should solve more problems than just the homework set so that you get more repetition, more practice, and form study groups. I mean, of course, you should get approval from your teacher and give credit on your homework, but usually teachers are happy to hear that. Like just put the names of your study group in the top right of your page. Like I worked with Jim, Sally, and Bob in the top right of your page, and I don't know, I think a good teacher will be like, great, good. Work with others more. That's a good thing. Create study groups. Was there another one? I feel like there was another one and I forgot it. But now I want to come back to theory of practice, because this is all application to math. Some of this is the theory of practice, I would say, spaced repetition. This is important in everything that you want to practice. Repetition is very important. Even if you learn something well the first time, you're going to forget it because we're humans and our brains are not as good as ChatGPT. we need to practice, and we need to repeat and come back to old subjects that we've learned in the past if we want to get good at it. I mean, really, I'm just like saying the same thing again, like repeat, do lots of exercises, do more than necessary. I don't know. I'm kind of talking about this all in context, but teach others. Like, this is something that you'll see in books that talk about the theory of practice. Last thing that's a practical tip is read the book Peak and So Good. I don't have my Newport book next to me, but I do have this one. I think his name is Erickson. Something like that. Give me 1 second. Ooh, stand strong. Perfect comment there. I love it.
Welcome to.
Hey, I'm so proud of myself. I was right.
So happy.
Yeah, Erickson. That's his name. This book is terrific. This is a book that summarizes all the research behind the 10,000 hours rule. So you may have heard of the 10,000 hours to become an expert rule. So this is the book that summarizes the real science behind that idea. Nothing wrong with Malcolm Gladwell. It's fantastic that he popularized the idea, but he kind of summarized this a little bit too much. So check this out if you want to learn about the theory of practice, because these ideas work exactly the same in classical guitar or classical violin or classical music or chess or like getting really good at programming and building iPhone apps or something. You want to teach others. Like in software, we call that mentorship, and being a leader, like an engineering leader. Spaced repetition is like, I don't know where that comes up. I mean, that's things like doing leak code. Like doing leak code is doing lots of exercises. I feel like software engineers don't practice spaced repetition enough, because it doesn't come to mind like a way that happens in no, there are ways. Anyways, I'm not going to get into the details, but yes, all of those techniques are also rediscovered in lots of different fields or applied. Like, some people know that about this theory of practice, it just keeps popping up everywhere. So, great question. Thank you. So, not SAT, but IMO. Dude, you're studying for the IMO? Are you kidding me? That's so cool. I would love to hear how that is. I never took any of the IMO exams, but I want to learn that math. I want to teach others. I want to be a coach for people doing the IMO. So you could be my student. Like, just keep showing up here, which comes to the next. I really hope I have chat replay on so people can read these chats afterward. I really hope so. Next time I'll figure out how to get chat on screen. But yeah, man. Yeah, you're my student. Free student. Like, and it's perfect. I don't do anything for free. That is my life philosophy. But you don't have to pay me any money. I am getting value because I'm teaching you. I don't have a student studying for the IMO, but I'm never going to get the experience of teaching IMO math unless somebody like you shows up. So thank you for being part of this stream and this journey. This is very exciting for me. I think that this stream is going to be super fun. Yeah, let me know when you have any books or any problems that you're solving, or anything like that. I'd love to hear what that's like, and I can look into it as well. But yeah, I couldn't find any friend that see mathematics as a pure subject, like they don't take interest. Perfect. I love that comment. I wish I could show it on screen really well, because that is exactly what this stream is about. It's a niche thing. Most people don't give a single fuck about. There's my one fuck for the oh well. Most people don't care at all about prime numbers or about theoretical linear algebra. Most people don't care. They want to calculate how fast a baseball will travel, or how, whatever. They want to build Skynet with artificial intelligence or something. But there are some people like you and me who love math in and of itself. And what's so cool about the internet and YouTube and finding these streams like this is that we can build a community of people studying pure math together. So I'm trying to build this study group that I wish I had when I was in college or when I was in your shoes. So awesome, man. Yeah, number theory it's the queen of mathematics. Okay, I gotta wrap up this stream. No, I've got a little bit of time. Okay, I think we could get through 2 problems probably. All right, so let's go this way and we'll solve this problem. So, I'm writing theory still. Okay, so we had, let's get some examples of what this means. A alpha I, alpha 2, ... alpha n. I'm going to switch to this notation once more. Let's get some examples. And here is a good tip for how to study mathematics. When you come across a statement in a book that you don't completely understand, try to create your... No, dude, don't worry. Like, this is fun. I love to talk with chat, and that was a very useful and interesting aside. Thank you. No worries. It makes it way more exciting for me, for the audience, for anybody else tuning in later on, I think. 'Cause that was a great conversation. Thank you. But when back to like connecting with what you just asked, how do you get good at math? Not just doing lots of exercises, but apparently cyan is my theory of practice color. Examples. Build your own. Like, when you're reading something like this and you're like, what the hell does that mean? Build your own examples. So let's not do a infinite dimensional or n-dimensional matrix, but let's simplify it to just this pretty simple one. A11, A12, A21, A22. Oops. So then this funny thing, AI11, AI22. Okay, so what does that mean here? That can mean a few different options. So, but we know that the second number, the second coordinate is 1. The second coordinate is 1. And we're multiplying it with another coordinate with a 2. So remember that the second coordinate is the column of a matrix. The first coordinate is the row of a matrix. And what this thing is saying is that I1 can change. I1 could be, it could either be 1 or 2. But if I1 is 1, then I2 has to be 2. Or we could swap them. I1 is 2 and I2 is 1. But we need to pick one. So like we can pick the number A11 and A22, or this thing could be the number A21, A12. Okay, so these are our options. We either multiply those two together or we multiply these two together. But it needs to be, as this thing says, just one element from each row and each column. Here's a good example of spaced repetition. One element from each row and each column. The next time that I write that sentence, I'm going to write it shorter. I'm going to say one element, each row, each column. That's like faster. It's like I remember the idea. It doesn't have to be a complete sentence, but one element from each row/column. Here is a much shorter version that says the exact same thing as the correct English full sentence. You write math with full sentences and with proper grammar, but when you're taking notes, you write it really short. And so part of my method of practice is to summarize and make things as succinct and short as possible, because it's faster, it's easier to remember one element per row per column, like one element per row per column. That means if I1 is 1, then I2 has to be 2. Like one of these has to be 1, one of them has to be 2. One of them has to be 1, one of them has to be 2. Okay. For a brief aside, in abstract algebra, there is the idea of the symmetry groups, or the groups of permutations. And you get numbers like 1, 2, 3, quote unquote numbers, or 1, 2, or maybe 2, 3. So I'm not going to go into details about that, but when I read this problem, I remembered, oh, this book is teaching it in this kind of way, in the most abstract, or in the more abstract ideas. We're going to get to this here. Like, I've seen where this book is going, and it's kind of more about this idea of permutations. Anyways, so I apologize, that might be confusing. My point is that here's a couple of examples, and then without writing the matrix, the whole matrix, I'm going to say in the 3-dimensional square matrix. Most books nowadays use A33, or like I forget how they write it. 3x3 matrix, something like that, I think. I think that, again, the book says that it's going to be they're going to be multiplications like this, where the first term is from the first column, the second term is from the second column, and the third term is from the third column. But then the rows can be different, or these can change. A11, A22, A33, or maybe the first one is the same, and then we swap these two. There's no more options there, so maybe we bump up the first item and then keep the other ones maybe sorted, like A21, A12. There's still more. What color were we using? That's a different. No, that's the same color, isn't it? A11, A something 2, A something 3. I think we still have a few more. A something 1, A something 2, A something 3. So we could keep the first number, or the first row, to be 2, and then swap, oops, this 3 should have, or that, whatever, 2 should have been a 3. So maybe the first number is still 2 in this element, and then we swap these two. And now the final option is going to be these with a 3 as the first number, and then these are all of the elements of the matrix of order 3. So I got a little bit better. I was able to skip some of these steps, like drawing out the matrix. I was able to come up with all of the terms just thinking about 3. And then I started seeing some patterns, like, oh, we're going to fix the first number, and then it's the transpositions of 2 and 3. Like, I started to see how this really is kind of like studying the number, or the, like, I could just write the, all I really care about are these red numbers. I1, I2, I3 equals 1, 2, 3. These are our options. 1, 2, 3, 1, 3, 2. 2, 1, 3. 2, 3, 1. 3, 1, 2. And 3, 2, 1. And then again we have 6 in total. Here we have 6 as well. This is the part that changes and is really the information that matters, because the blue part is all fixed in each of these terms. So, okay, that's cool. All right, now I understand what this note from the book means. Let's move on then. Oh, my cat. I don't know if I've introduced Luna yet to this stream, so here's a good opportunity to take a break. All right, be right back. Luna. Luna. All right. Have I completely lost you, Stand Strong, or do you feel like you understand some of this? Either answer is completely okay. Sir, sorry, sir, I would have to leave because of dinner, but it was a great session. I will make sure to watch the next one. Awesome, man. Thank you for tuning in. It really means so much to have company and an audience for this. So thanks for tuning in. It's nice to meet you again, and enjoy your dinner. I hope you learned something interesting from this. Yeah, thanks for stopping by. Cool. So I'm going to continue, and I'm just going to wrap up this problem and maybe just write down the next problem. Unfortunately, we didn't get to a problem that I haven't seen yet, but that's fine because I did solve this one myself. What's the name of the cat? Luna, Luna. Oh, you're here for 5 more minutes. Great. This is really cool. What do you want to do? Like, do you know what kind of work you want to do? Do you want to do engineering, or do you want to become a mathematician? I take it that since you're studying for the IMO, you're still in school. But correct me if I'm wrong. Yeah, she's so cute. Luna, Luna. Okay, so I understood, and now I understand what that sentence means. Let's keep going. So now there's like a little bit of stuff that he's writing that exactly matches. Why don't I just show this to the camera so y'all can see exactly what the textbook says. Determinants of order n. Suppose we are given a square matrix, an array of n squared numbers, and then the number, so it's a square matrix. The number of rows and columns is called its order. We did that stuff. Now we're here. I just wrote down this sentence, and we got some examples there. What else is going on? Blah, blah, blah. They appear in different rows. Represent some permutation of the numbers. That's exactly what I just discovered. I just realized, it's a permutation of those numbers, 1, 2, ... n. That is what I just realized and discovered live, or while I was first doing this problem. Next, it says, by an inversion in the sequence. So now we're going to get to what I'm expecting next. We mean an arrangement of 2 indices such that the larger index comes before the smaller index. Okay. The total number of inversions will be denoted n blah, blah, blah. For example, there are 2 inversions in the permutation 2, 1, 4, 3. 2 before 1, 4 before 3, so that n 2, 1, 4, 3 equals 2. Okay, so why am I reading this part? Why do I know it's relevant? It's because I skimmed the book and found here is where he talks about the sign of the terms. And so I see, I need to understand what this n thing is, which brings me backward, until I got to something I do understand. So now, I'm not learning this for the first time live. You're in 10th grade, but love mathematics. Heck yeah, dude. That makes me so happy, because I wish I saw this stuff in 10th grade. That's really cool. So you want to study mathematics. This is the channel for you. There are other good math channels on YouTube, but I want to build the best math channel on YouTube. Why not? Let's go big or go home, right? Cool. So let's see. I just showed all that to the camera, so I'm going to skip ahead just a tiny bit and just take some quicker notes. So we've got some stuff about an inversion of, what does he call it, a sequence? And he says it's the number of times a number appears, the number of times a larger number appears before a smaller one. I had to wrap my head around this a little bit because I was like, is that exactly right? But I remember from a representation and group theory class that it was something like this, but again, it was studying these like quote unquote numbers as like a multiplication of these sequences or something. But yeah, like I haven't seen this exact same idea of inversions in linear algebra before. So I was like, oh, this is really cool. Okay, so we're getting the linear algebra explanation of this stuff. So, where are we? So we've got an example that n is the number of times that that numbers are swapped. Swapped is my head thinking another word for inversion. We have an example that 2, 1, 4. So all of this math is going to be advanced for you if you're in 10th grade, but that's okay. If you just understand like a little bit of what I'm talking about, like that's gonna be really good for you, I think. So he says that this is 2. Okay, why is that? Let's figure out why. Well, he said that it's because it's the number of times that of two indices such that the larger index comes before the smaller index. The total number of inversions will be denoted by n ... So the total number of times that a larger index comes before a smaller index. So 2 is greater than 1, but 2 is smaller than 4, and 2 is smaller than 3, so that one doesn't add to our total number. So there we found 2 is before 1, 1 is before 3, or 1 is before 4, and 1 is before 3, so 1 is fine. There's no transpositions with 1. But then 4 is before 3. 4 is greater than 3. So there are 2 inversions in this sequence. 2, 1, 4, 3. There are 2 larger numbers before smaller numbers. Okay, that's a good example. And then another example is n 4, 3, 1, 2, and that equals 5. So let's count the 5. 4 is before 3, 4 is before 1, 4 is before 2. 3 is before 1, 3 is before 2, and that's it. 1 is before 2, and that's correct. So there's all 5. Great. Now, continuing on, blah, blah, blah. All right, let's write this out verbatim. If the number of inversions in the sequence, he writes alpha 1. I don't like alpha. I'm going to use I1. If the number of inversions in that sequence is even, he writes, we put a plus sign. We put a plus sign before the product 5. So that, what is 5 again? What the heck is 5? I wrote it somewhere. I know what it is, but I just want to show it again. Here it is. The term A alpha I. Oh yeah, that makes sense. So here I'm going to like rewrite just for myself in my preferred notation. I1, 1, I, N, N. If the number of inversions, blah, blah, blah. If odd, we put a negative sign before it. In other words, the sign, which I know in another context is used, we use the letter bye. Yeah, nice to see you. I know in another context we use the Greek letter sigma to write down the sign of these terms. Sigma is -1 raised to the number of transpositions, the number of inversions. So I1, IN. And this is like, this finally is the thing that we want to understand to solve the problem that we wrote down somewhere. Here's the problem. Let's give it like a big old square so that we know that this is what we're trying to get to. With what sign do those terms appear in the determinant of order 6? Okay, so why don't I see if I can do something fancy. I really love this app, by the way. I am an app developer, and I appreciate how beautiful Notability is. Although right now this is tough. Okay, I'm going to miss some of the box, and that's okay. So I can copy that down here, paste it, and we got like another duplicated version of that same problem statement. So now we understand what this exercise is asking of us. So we want to calculate -1 n of the this took me a second to like really understand and make sure, but yes, it is. Oh, okay. Yeah, there's a first step that I needed to understand before getting here. Okay. Problem A within problem 1 is A23, A31, A42, A56, A14, A65. Okay, so this is the term that we're trying to understand, but one thing is that the standard form that he wrote in standard form 5, this always has, it goes in order where the first element has a 1 as a second coordinate, which is the column. At some point you don't think about whether they're rows or columns, it doesn't matter. It's like the first index or the second index. But here, these are not in the same order. Like the first one has a 3 as a second index and a 1 as a second index for the second term. So that, now I'm going to use the fact that maybe you have to double check yourself on, that in linear algebra, we can assume that multiplication is commutative. In linear algebra, A times B equals B times A, but that's not always true in other types of algebra, and we won't get into that. But here, I know that I can rewrite this entire term as a 3-1, a 4-2, a 2-3, a 1-4, a 6-5, a 5-6. And now this is in standard form 5. Now, therefore, the problem is asking us to calculate this, where n, now I can write down 3, 4, 2, 1, 6, 5. Okay, and we learned how to calculate what n of that stuff is. We're going to count the number of inversions. 3 is before 2, 3 is before 1, and then that's it. 4 is before 2, 4 is before 1, and then that's it. 2 is before 1, that's it. And then 1 is less than 6, but then the last one that we're missing is 6 is before 5. So, if I calculated all this right, which I think I did, we've got 6 in total. Then -1 raised to the 6th power is +1. And voila. Hell yeah, QED, there's the answer to part A. And I think that I'm going to leave it at that. I'll let the viewer, the audience, stand strong, you in particular. I'll leave part B as an exercise for the viewer. And I'll say that something I love about this book, and one of the reasons I picked this one when I was trying to find a new linear algebra book, I saw some reviews mention that something that they love about it is that most of the answers, most of the problems are solved in the back of the book. So we can see right there. All right. Answer, part A, plus. We got the right answer. Part B, exercise for the reader. Why is it plus? So, which book is this? This is Shilov, Linear Algebra by Shilov. I should absolutely set up some referral links soon, but it's very cheap. It's like, I mean, cheap is relative, but compared to other math books, this one is like $15 or $20 US, whereas my other books were like $80. So, all right, let me just write down. Exercise for the viewer is A32, A43, A14, a 5-1, a 6-6, and a 2-5. That the sign, I'm gonna give you all a to-do or exercise to the reader. Show that the sign in determinant is positive. And it is the exact same process that we did in this first part. Done. Thank you for watching, everybody. This was a really fun stream for me. This one was just a little bit meatier on the actual math compared to the last two videos. So I think this was super fun. Thank you, Stan Strong, for watching. And thank you to the audience for watching as well. Anybody who sees this after the fact. All right. Bye, everybody. This was super fun. Bye. Have a wonderful dinner. And, oh, yeah, question. By the way, what would be the topic of next class? I don't know yet. I think probably we did 3 lectures, 3 videos on number theory, easy and medium. Now we just did 1 on linear algebra. I think I'll do another one on linear algebra. But then the next one this is kind of an advanced linear algebra. Next time I'll find an easier linear algebra book or problems to work through. So more like this useful, where was I writing it? More like the useful applications of linear algebra. I'm going to find a good book on that. And so next time it'll be a little bit more applied and computational as opposed to theoretical like this one. So thanks for watching. All right, have a wonderful day.